Hello everyone, welcome to my talk. First of all, I would like to thank Professor Stephen Winter from the University of Melbourne, who invited me to give this talk. This is Li Pingyang, Assistant Professor of Geographic Information Science and Computer Science at the University of New Mexico. My research focuses on geospatial artificial intelligence and visualization of geospatial big data. I direct the Geospatial Artificial Intelligence Research and Visualization Lab, named the GLL Lab at the University of New Mexico. My talk topic today is advancing computer vision and machine learning using topological graph-based representations and methods. Before we jump into the major content of my talk, I would like to share with you some very inspiring quotes from a few very important figures in computer vision. When David Marr at MIT moved into computer vision, he generated a lot of excitement, but he hit up against the problem of knowledge representation. He had no good representations for knowledge in his vision systems. I think the way we are doing computer vision is just wrong. If we want machines to think, we need to teach them to see. As nature discovered early on, vision is one of the most powerful secret weapons of an intelligent animal to navigate, survive, interact, and change the complex world it lives in. The only path to build intelligent machines is to enable it with powerful visual intelligence, just like what animals did in evolution. To know me a little bit more before my talk, you can get a glance on background here. My geoscience background comes from my Bachelor of Science and Master of Science in China. My spatial informatics and computer science background are from my PhD and postdoc training in the USA. I started my professorial journey since last January. I will now briefly introduce my PhD research. Two major components in my PhD research include semantic modeling of indoor space and the development and implementation of computational algorithms for navigation graph generation of indoor space. For the semantic modeling of indoor space, the major technique I use is called ontology. There are 4 levels of ontologies: upper level ontology, domain ontology, and task ontology, and application level ontologies. The upper level ontology includes various general concepts like size and affordance. The domain ontology indicates the structure of the indoor space, physical space, such as room and corridor. The green nodes represents tasks such as node link, which is the subclass is affordance. The white nodes represent bottom level application ontology concepts such as leaping the instance of pedestrian. This slide provides the list of computational algorithms that developed and implemented in my PhD dissertation. So I would like to highlight one concept called local kernel, because later in a minute you will see local kernel is not only useful for the indoor space navigation graph generation, it can also be useful for some computer vision tasks. So to understand the local kernel, first we need to know what's the kernel. So a kernel of a polygon is the set of all the points that can see the entire of a polygon. For example, the orange region is a kernel of the black polygon, because all the points in this region, you can see the entire of the polygon. So, but not every polygon has a kernel. For example, this U shape obviously doesn't have a kernel, right? There is no single point you can see the entire of the polygon. So in my dissertation, I proposed a concept called local kernel. So for this blue, there are 2 local kernels for this U shape. One is a blue shaded polygon, and then one is a red shaded polygon. So for this blue shaded polygon, we can see it can see the blue hashed areas. Even though it cannot see all the entire, but it can see most part of it. So the red local kernel, they can see the red hashed areas of the U-shaped polygon. So we can see the local kernels can be useful for the image analysis. This is the kernel of the X-shaped polygon. The W-shaped objects don't have a kernel, right? So because there is no single point, you can see the entire W shape. So there are 3. We can build the 3 local kernels for this W-shaped image. I will come back to this in a minute. So a major piece of work in my PhD dissertation is the generation of navigation graph for indoor space. So we input a 2D flow plan of indoor space. Then use my algorithm methods, we can generate the navigation graph corresponding to this 2D flow plan. So this piece of work is published in this IGGS paper. If you are interested, you can welcome to check it out there. So like I mentioned earlier on, the local kernel I proposed in my PhD can be useful for the indoor space navigation graph generation, but it can also useful for the image analysis. For example, it can be used for the skeleton extraction. This piece of work is published in this my recent computer vision and pattern recognition workshop papers. You are welcome to check it out if you want to know more details. Now let's take a quick look using how this algorithm works using a straightforward example. Input image, we get the contour of the image. Then by extracting the corner points of contours, we build the structure graph from the contour. From the structure graph, we generate the local kernel, two local kernels, the blue shaded areas, local kernels for this polygon represented by the structure graph. Then we use the local kernels to partition the original polygon represented by the structure graph. We can see it's partitioned into 5 polygons, 3 orange and 2 blue polygon. Then for each sub-polygons, we get the centroids. It's easy to compare because they are all convex polygons. So we get the centroids of each polygon. Then we get the graph of which connects all the centroids of this the centroid of the subpolygon. We can see there are two. We need to find out the leaf node. For those who are not familiar with the graph theory, the leaf node in graph theory means the node only have one neighbor. So in this graph, we have two leaf nodes, right? This one, because it only have one neighbor, and this one, it only have one neighbor here. So for the leaf nodes, we need to extend its and then intersect it with its polygon. We extend this edge and intersect with each polygon. Then we can get this graph representing the centroids of nodes and its intersection with the original polygon. Then we can get eventually get the skeleton graph, which is the skeleton corresponding to the input image. Now I will provide the overview of my rest of my talk. This slide shows the roadmap of the rest of the talk. So I will first briefly introduce motivation, and then I will introduce you some major concepts that will get you prepared to understand the rest of my talk. Then I will introduce my very simple and powerful image representation I proposed to tackle some computer vision challenges. Then followed by 2 applications using my image representation. One is image classification, one is line segment detection. Finally, I will conclude my talk with some further potential applications of my image representation. So to understand the rest of my talk, I think this brief conversation between the human and the machine will be very helpful. Bob, can you tell me whether this design has been patented or not? Sorry, sir, it's not solved yet. I cannot see that image well as I grew up with natural images. Look at that scary zigzag noises. This is one of the bottlenecks that makes me cannot see the image well. So my work is motivated when I talk about photo search versus drawing search. What is this? When you ask Google, they can actually tell you pretty good. They can find the similar images that matching the input image. But when you ask Google search engine, what is this? Google cannot tell. Google can only find copies. So the overall goal for the project I worked well was at the Los Alamos National Laboratory is the diagram image retrieval, identifying and return visually similar images for a query diagram image, for example, pattern images. So let's see. Before I'm going to conduct the work, I need to check some basic computer vision techniques. So let's first see the challenges when we come into the pattern images processing. How many straight line segments you can see from this simple diagram image? 1, 2, 3, 4, 5, 6, 7, right? If we do not count the curves. Guess how many straight line segments machine see? We can see the machine sees many teeny small segments. You can see it's, if I remember correctly, it's about 150 tiny line segments. So let's see the same diagram image. How many corner points you see? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If we do not count the corner points on the curves. So guess how many corner points machine sees? When I use the computer vision algorithm to do this task, I need to input one of the parameters, ask me how many points you want. This is not robust, right? The algorithm. If we already know how many points we want to return, why we need to use, the computer vision techniques to do this? So when I set the parameter as 100 points, it returns these results. The green points represent the corner points the algorithm detected. Then let's see. If I set the points as 50, the parameter corner points I want is 50, then we can see this return this amount of corner points. Before I go into the major container method, I would like to introduce some concepts that will get you prepared to understand the rest of my talk. First concept is called data representation. So what's data representation? It's the form, how the data is stored, processed, and transmitted. For example, this image we saw the digit 8. In the computer, they actually stored as a matrix like this. Then the performance of machine learning methods is strongly dependent on the data representation features to which they are applied. For example, the same, they represent a river branch. You can use both the raster representation and also a vector representation. The major difference between the raster and vector representation is when you zoom in, you see the pixels, but when you zoom in the vector data, you will not see the pixels. Then another concept I want to talk about is the feature engineering. If you want to know more about feature engineering, you can check my recent paper here. Some machine learning projects succeed and some fail. What makes the difference? The most important factors are what features are selected and used. So machine learning usually requires feature engineering, but deep learning doesn't. However, deep learning requires a large set of annotated data. This is kind of, to some extent, it's the manually annotation is kind of label intensive. It's another way, we can view it's another way of feature engineering, right? Because it's both feature engineering and manual labeling data takes time, label intensive. So the next concept I want to introduce is image skeleton. If you want to know more about this, you can check my recent paper, CVP paper here. So a central line is, an image skeleton is a central line, 1 pixel wide representation of an image that present in an image. So let's say this example, this is original input image. Now the image skeleton is corresponding image skeleton. This is a seen version of the input image. So the skeleton emphasizes the topological and geometrical properties of shapes. The last concept I want to introduce you is called topological graph. So it's if you want to know more about the topological, you can check my paper published here. And it's a set of nodes and edges. A graph contains a set of nodes and edges. The nodes can represent objects, and the edges represent the relationship between the nodes, the connecting nodes. So it's a topological graph is an intuitive, powerful data structure and a data representation framework because it can capture the topological relationships and the spatial arrangement among entities that are present in an image. For example, you may not understand the topological graph concepts explicitly, but we use it a lot in your everyday life. For example, check this road map. road network, we can see if we view this is a bus stop, then if this two bus stop is connected, then we can use a line to connect them, which is called edges here. Also, we can use a graph to represent a social network. For example, if each nodes here represent a Twitter account, then if you know this is your Twitter, this is your friend Twitter. If you have connections on the connecting on the Twitter, you can have a link, an edge to connect them. So now I will talk about the effective image representation I proposed. The image representation proposed is called a skeleton graph. So it's a topological graph generated from image skeletons. You are already get prepared what's a topological graph, right? It's a set of node and edges. Then what's a skeleton, right? It's a single version, 1 pixel wide of the single version of the input image. So let's see the many proposed image representation. This is input image. Then we can see we first generate the skeleton, which is a single version of the input image. Then we generate the skeleton graph from the image skeleton. We can see how this skeleton graph is generated. For each point in the image skeleton, okay, we represent the nodes. Then if they are the neighbor nodes, then in the image skeleton we use a line to connect them. It's simple, right? Again, input image, a single version image, which is the image skeleton. Then we get the image skeleton graph from the image skeleton. So again, each pixel represents nodes in the image skeleton. And if they are neighbor pixels in the image skeleton, we use a line to connect them. You know, this all is neighbors. We use line to connect them. So this work image skeleton representation is published in my recent paper here. So now it's simple, right, and intuitive. Now I will show how powerful the image skeleton representation I proposed. So for the first application is called image classification. Let's see the major image classification workflow using the topological graph features. It's extracted from the image skeleton graph representation I proposed. This piece of work is published in my recent paper here. And we first input images, then we do the image skeleton extraction. Then we do the skeleton graph, okay? This is very simple, right? Very straightforward and intuitive. You already understand this workflow. Now, once we get the skeleton graph, we will extract the topological features from the graph. For example, cycles. So this, for example, they have one cycle. This should have two cycles, but they are not close, so they are detect one cycle here. So let's see one more example here. So the digits 9, we can see in this skeleton graph, they have one cycle. For this the handwriting digits 9, they have two cycles. But do not worry, if we have enough data sets, you know, the machine learning algorithm will be able to detect they are both under the category digital 9. So the next step is we need to train and evaluate machine learning models. So in this piece of work, we use multiple machine learning models, random forest, support vector machine, and neural network for image classification using extracted topological features. Then we can fit it into. We also do the hyperparameter tuning, the k-fold cross validation. Then we evaluate the model using the best parameters. So the advantage of our approach is it gives the competitive results with a very small set of training data, and it's faster to train and are much less sensitive to hyperparameter tuning. So let's see, the one example here is we compare let's see some experiments and results. We first run the support vector machine learning algorithm on the hands-on writing digits, the minutes data sets. Then we compared with against using our topological features extracted from the skeleton graph. Then also we'll use the hog features, which is called the histogram or oriented gradients. This is a well-known hog features in computer vision area. So let's see, when we use the run the support vector machine using hog features, you can see this solid line means best parameter, best model, and this dashed line means the baseline model, which means the default parameters. Now we can see there is a large room between the baseline and the baseline. This is not good thing. When you that means this model is very sensitive to the hyperparameters. But when using our topological features extracted from our skeleton graph representation, you can see the baseline model and baseline model is there is very narrow. Very narrow gap. That's a good thing. That means the data scientists do not sit there to the long time to do the select the feature engineering and get the best parameters. Okay, the next is we can compare to the computation time. You can see when the SVM model using the Hawk features, the best model takes a very long time to train. Then for the baseline model, it still takes a much longer time than ours. You can see for the baseline for our best model when we're using a topology features extracted from our skeleton graph, it takes a very short time to train. Or you might ask, maybe your topology features are tailored for the support vector machine learning model, but to demonstrate topology features works for other machine algorithms. We also run the same data sets, hands writing digits, minutes data sets on the random forest algorithm. We can see even though it performs much better than the support vector machine learning algorithm, we still see for the baseline model and best model, they are still much larger gap compared with our when we use our topological features. Okay, say our methods are much less sensitive to the hyperparameter tuning, which is a good thing. So now let's see the times to train the random forest when using Hawk features and when using topological features we proposed. So you can see the random forest when you're running on the Hawk features, the best model takes a very long time to train. Then the baseline model still takes when we use our model, even the best model is only takes much less time compared with the random forest when running with the Hawk features. So you also run this results on another machine algorithm called neural network. We can see when we use our topological features, our methods, when have a very small training data set, which is 100, 500, they already reach pretty good results. But when we use this when we use the Hawk features, they need to much larger to reach the good training accuracy score. And you can see neural network. Everyone knows neural network is very time consuming when it come to the training. So you can see when you use the neural network Hawk features, it takes much time. For the best model, it takes a very long time to train. Even for topological features, it still takes a much longer time to compare with random forest and also the SVM. So, but we can see it's even for the time-consuming neural network, our methods when using topology features we propose is still much less time compared with the Hawk features. Okay, if you need to know more about the piece of work, check my recent paper here. And now I will show you the last application, line segment detection using the image presentation I proposed. So we can see the input images here is actually from pattern images. So we input the image, then we get this is what humans can see. This is manually labeled by the humans, the green lines, the line segment. But this is what the machines can see. This result is coming from the state-of-the-art line segment detection method called LineLit. It's published in IEEE TPAMI journal, which is the #1 journal in the computer vision deep learning area. It's published in 2017. You can see the result. There is a lot of tiny lines segments. So our line segment detection workflow using our TGGLines, we name it TGGLine, topological graph guided line segment detector. So we input the diagram image, then we do the image skeleton instruction. This work is published in this manuscript. Please check it if you are interested. So then we do the skeleton graph generated from the image skeleton. So we zoom in detail, you can see. Then we can, from the skeleton graph, further remain detail of the skeleton graph. Then we detect the cylinder nodes. Then we can see these tiny nodes. the red nodes or junction nodes that means it has more than 2 neighbor nodes. Then it's the junction nodes. The blue nodes means the turning nodes. These red nodes in junction nodes because they have more than 2 neighbors. The blue nodes represent turning nodes. That means it has 2 neighbors, but it has sharp turning. So after that we use the salient nodes to segment the scaling graph to passes. Then we can see that here the image scaling are segmented to 3 segments: the orange, pink, and the gray. Then we use the Douglas-Book algorithm to simplify passes organized by the line segment connected graph. So let's see, this image shows the detected line segments organized by line segment connectivity graph. So you can see, we can see if there are all the segments detected in our methods, they are organized by another graph called a line segment connectivity graph. So this nodes represent this line segment and this line segment, they are neighbors, right? Because they connected through this node. Then we use one node to represent this line segment, the red segment, and one node to represent this blue segment. Then we use a line to connect that to indicate these two line segments are connected. So let's see some experiment and results. This line segment detector is named LSD, is the very classical well-known line segment detectors in the literature. We input the image, then we can see when you use the LSD, the line segment detection, the results are like this. Then when we use LENIT, the state-of-the-art methods for the line segment detection, we can see the results is pretty poor, right? They have many broken line, teeny line segments. But when you use our TGGLine methods, it's very crispy. It's very good. Then let's see another example. Here, we input this the pattern image. Then when we use LSD, the results is not good. When we use ED-line, another state-of-art method called edge join lines, the results is much poorer compared with LSD. You can see a lot of lines are missing and they are broken line segments. When you use our methods, it's very well, much better compared with the state-of-art methods and the classic methods for the line segment detection. When you use the TGGLines, this is a column shows our results. This shows the input image. Then this shows the ground truth where humans manually label them. Then we compare with the full state-of-art methods for the line segment detection, which called PPHT, progressive probability whole transform, LSD, and ED-lines, as well as LENIT. Let's see, all methods perform the best. Let's check more example here. Our methods performs much better than all the other state-of-art methods. Then the advantages of TGGLines are TGGLine outperforms the full state-of-art methods, PPHT, LSD, ED-line, LENIT. And in our methods, we only require one parameter, and it's adaptive. So line segments detected by our TGGLines are organized by a line segment connectivity graph. So not a loose set of segments like other methods detected. So you may ask why TGGLine works so well? The main reason is that the state-of-art methods are failed is because the persistent zigzag noise. You can see this is in detail, so you can see there are zigzag noises here in low quantity pattern images. So the state-of-art methods are built on either edges or local gradients. All TGGLines can handle zigzag noises very well by leveraging the topological and geometrical analysis. And our methods does not rely on edge detection or local gradients. That's why our methods works very well. Again, this piece of work is published on this paper. Now I will conclude my talk. I have introduced the topological graph-based representation for intelligent image data analysis. I have demonstrated our proposed representation is very effective for machine learning and computer vision. Many applications can build on top of our topological graph-based image representation. For example, extraction linear features from remote sensing images. The vectorization of hand drawings. Then we take an image of hand drawings and then come back to vectorization, and then based on the vectorization version, you can coloring the different parts of the drawings. I would like to thank the grant I received when I was at the Los Alamos National Laboratory. I also would like to thank my summer intern graduate students, Ming, Catherine, and Manish. Thank you for watching. Feel free to contact me if you have any comments, questions, suggestions.